No, no problem. Okay, so this is a case study about the Illinois Basin Decatur project. So I advance with the buttons. It's not advancing. Oh, a clicker. Okay. Which one?
Maybe I will sleep in the last. That's weird. It totally worked in the last one, I promise. Yeah, they should work.
Okay, I'll use the arrows.
Okay.
All right. So
Oh, that may actually work now. But
no,
yeah, there you go.
I'll use the arrows. Okay, so you may just to sort of orient you on the current initiatives to accelerate CCUS in the U.S. There started in the beginning. There were a lot more than, well, maybe a couple more than this, but this is what it looks like now. And we're in the Midwest Regional Carbon Initiative, and these are the states that have the Illinois Basin in it. And that little tiny black square there is the Decatur project, and the square is bigger than the project itself. It's not to scale. And I just wanted to sort of explain the progress for what we're doing in the Illinois Basin. So we started with the Illinois Basin Decatur project. That's the IBDP for short. That was a demonstration project to show, whether it can be done there. And it's a partnership with Archer Daniels Midland ethanol plant. And at the same site in Decatur, Illinois, the second project was the Illinois Industrial Carbon Capture and Storage Project. So there are 4 deep wells there, which I'll show you later in this presentation, 2 injection and 2 monitoring wells. And the goal for that one, this one is actually commercial. I'll give you some more details about that in a minute. And then we go into there's a lot of other carbon safe phase 1, phase 2 projects in various stages at the moment. So the goal is to find storage in the entire Illinois Basin and look and see if we have, if it's feasible to put more than 50 million tons of CO2, largely in the Mount Simon sandstone, but we have a couple of other reservoirs that are also candidates. And so we have at least 2 projects that are starting to get toward phase 3 injection permitting, in addition to the IBDP and ICCS projects, where we're going for permits for additional class 6 injection wells. Okay, so here's the 2 brief description of the 2 projects there. The IBDP project, as I said, was a demonstration project. We injected 1 million tons there over 3 years. That project ended in April 2020. We uploaded the report and all the data is publicly available now in June 2021. So, and I know lots of people have been downloading it because I've been getting questions about how to use it. We found out there were some things that we forgot to upload that we're still uploading. But just about everything is there. So we're interested to see what people come up with that we didn't have time to do, or that is different or better than what we did on this project. The Illinois Industrial CCS project is still injecting. And I have down there that they've injected more than 2 million tons. It's actually approaching 3 million tons. The goal for that one was to inject at about double the rate. They're not quite double right now, but they are getting rid of all their CO2. All right. So here's a map. What you're looking at on the right side is is topography on the top of the basement, and a lot of those brown lines there are faults, but a lot of them are actually identified as anticlines and synclines that may have faults underneath, but the structure is subtle enough that we haven't confirmed all of those. And also most of that information is coming from wells. So if we didn't cross the fault, we don't know for sure that it's a fault, but we do know the beds are dipping, for instance. And the Mount Simon sandstone is the target. It's got the cyan rectangle around it. And the blue labeled units are potential reservoirs, and all of the ones in the white red outline white boxes are the seals. So as you can see, there's 3 regional seals above the Mount Simon. This is sort of the crux of what I'm going to talk about, the active and passive seismic data that we acquired and analyzed at the site. So you're looking at the 3D seismic data acquisition footprint there. It's a very small footprint, so you can see at the bottom that the length of this image is only 4.3 miles or 6.9 kilometers. And all of the green, whatever color that is, squares are the USGS seismometer stations that were installed 18 months after injection started. And there's some red triangles. So there's two networks. The red triangles are the ISGS seismometers. So we have five seismometers. Some of them have failed. So we're looking at trying to replace them. So all of that, the seismometers are still collecting data. And I'm sure you can, if you know when there might be larger earthquakes, you can go in and collect the USGS data from that, but they haven't published a catalog since injection ended at the site. The sort of red to orange to yellow, purple to orange to yellow dots there are the induced seismicity. So when you look at those, you think, oh, well, that just is showing where the faults are in the subsurface. You can see where the Archer Daniels Midland plant is in relation to where the induced seismicity is developed. And what I'm going to show next, where that line I just appeared, is a cross-section through the 3D seismic. All right, so our goal, like if you want to do seismic imaging to try to characterize the reservoir, it was fairly easy to map out tops, but faults were another thing, right? So we actually, the originally processed seismic, we couldn't even see what we see right there, right? So now you can look at that and say, okay, maybe there's some faults in there. And so we came up with a fault interpretation that we use to characterize the reservoir. Then when we did this reprocessing, we also the company that we use also did a porosity inversion, which we thought was great because it helped a lot for the for reservoir characterization. So the blue there, all of the blue is the low permeability. So the blue at the top is the Eau Claire shale top seal, the first primary top seal. And the blue at the bottom is the Precambrian basement. So you can see that the low porosity matches up with both of those. So the blue is, either granite, I can't remember. Granite-rhyolite. I was going to say somebody said gabbro today, and it stuck in my mind. Granite-rhyolite and or shale, right? And the dark oranges are the reservoir rocks. And I'm going to zoom in. Well, this is the same box that I showed on the other one. So to me, this doesn't actually help, as I said before, with the faults, but it does help with the, following the stratigraphy and understanding where the best reservoir is. But this box is, I'm going to show in the next slide, 2 times vertically exaggerated, because I want to zoom in some of the details of the structure that we did get out of this porosity inversion. So the interpreted tops are on there. So the Mount Simon A, the lower part of the Mount Simon down here is where the injection in the first well, the CCS well, 1 well happened, just above this Argenta, which is, you can call that a bottom seal, right? So it's a much lower permeability porosity argillaceous sandstone here. And we interpret this as a fault. We think that's a fault. And then we interpreted it as a fault. And then we looked at the reprocessed. We have a 3D VSP that was reprocessed there. And it actually does highlight or show indications of a fault right there. But the thing that was most interesting about this is if you look at this Argenta, you see that there's this basement high that was identified in the interpretation. There's this basement high on top of the Precambrian. And on top of that, it looks like either this Argenta is very thin or missing. So the story that I'm going to build here as I get through the rest of the slides is that has something to do with why we got the induced seismicity. This is our fault interpretation. These faults, again, have not been, they're interpreted from the seismic, from people who are braver than I am to commit to there actually being a fault at these locations. But I was convinced by the interpreter's methodology that there's justification for putting faults there. but they don't have very sort of coherent indication of structural style or anything like that. They have very low displacement, vertical displacement, which is the main reason why we had trouble interpreting them in the first place. On this displacement versus fault length diagram on the left shows that the maximum displacement on any of these faults is 60 feet, right? So it's very small. So they could be strike slip faults, but we don't have a way to confirm or validate that as well. But where you can see the displacement, this is about the best we could do in terms of the fault interpretations. And so, you know, when you're doing this interpretation for reservoir characterization, you want to know where the faults are so you can identify the ones that might lead to induced seismicity. Most of these faults were interpreted in the reservoir. Some of them were extended down into the basement where it looked like they were connected to the reservoir. And we wanted to make sure that they weren't coming up into the top seal. This final fault model, I'm going to call it model because it's not exactly where everything was interpreted. The geomodeler who built the faults kind of prettied them up so that they had smooth edges, but I don't think that we necessarily can extend them up as high as most of them are. And there's no indication that these faults actually get anywhere close to the top seal. And so the other thing we want to know is, you know, like I said, we want to know where the faults are so we can say whether we should expect induced seismicity. But once we got the induced seismicity, it sort of compounded the uncertainty. I'm going to show you that next. So here we go. This is the same cross-sectional area. I'm just going to show you two cross-sections that are close together. You can see the location map in the lower right. The thick bar is where we're looking in this cross-section. And I've projected the induced events onto the seismic line from about 100 meters away. And they kind of sort of match up with where the faults are, but as the thing that I'll discuss it in more detail later, but you can see from here is that the induced seismicity is all in the basement, which is what we have seen in other locations. It's not in the reservoir. And maybe, so this fault, let's see, this fault right here might have some, this is the only one that I would interpret as having any real relationship to the induced seismicity, but the relationship it has is that the seismicity is coming toward that fault and terminates there. So it doesn't look like the fault we interpreted was the fault that was reactivated. Here's another, just a little bit, you know, further to the east, the same thing, more seismicity that looks like maybe it's connected to the faults, but the faults we interpreted don't match up with the induced seismicity. Okay, I want to take a little segue over to natural seismicity in the Illinois Basin. And of course, we're relatively close to the New Madrid seismic zone here. And so this, we were talking about this at lunch, our geology stops at the border. And so we have a lot of seismic events historically since 1795 in the southern part of Illinois. So that's much more seismically active than the area where the IBDP project is located. And I looked at historical seismicity within 100 kilometers of the IBDP and only found a few historical earthquakes that are bigger than, I think in this case, none of them were bigger than magnitude 3. And we're looking at, you know, a couple hundred years worth of earthquakes during that period. So it's a relatively low natural seismicity zone where the Illinois Basin Decatur project is located. And just for reference, for those of you who may not be that familiar with earthquake magnitudes, I like to show this chart that I took from the British Geological Survey website some years ago to show you what kind of energies we're talking about. So if you're looking at small events, -3, -2, the energy is, you know, like if you drop, what is that, 6 apples, 20 centimeters, is a -3 magnitude earthquake. I don't know anything about slingshots, but I take their word for it that -2 is energy in a powerful slingshot. And when I first looked at that, I said, 100 kilogram person drops down 2 meters. What could that be? Well, that's a 100 kilogram person. They can definitely jump 2 meters. And then here's TNT. So we're starting to get into earthquakes that are A little bit, you know, once you get to, this is where I define microseismicity. Some seismologists use magnitude 3 and below, but I'm going to keep it below 1 and below, because that's kind of the range that a lot of hydraulic fracturing happens until they get one that's bigger, then it's an earthquake. But 1 and below that is generally going to be in the range where people can't feel it. Okay. And I also wanted to do a really quick comparison to wastewater injection. So as I said, we injected over 3 years, 1 million tons of supercritical CO2 in the IBDP well, which means that we injected over 1,000 square meters per day. And there was a bit of induced seismicity, no felt seismicity, right? So it's induced microseismicity. And the second well is the injection is averaging 1.7 times the injection rate of the first well. So 1,950 cubic meters per day over 3 years. We have less induced seismicity, and I'm going to explain that in a minute. But the purpose of this chart is to show you that our injection rates are approaching some of the injection rates that we see for wastewater injection, and we're not getting big events there. So here in East Texas, after 1 year of injection at 2,000 cubic meters per day, you can get a 4.8 magnitude earthquake. But there's something similar about what's happening in the Illinois basin to what's happening in the Williston basin, where they can have really high injection rates, and they don't have a lot of, they don't have felt seismicity there. So back to this map of the seismicity. On this, what I wanted to point out is that, so you see these events that develop, they are temporally and spatially developing. So this is where the first cluster sort of started, and they continue to build over time for the most part. But this is the sequence, right? And you can see right here is the injection well. So they don't start near the well, they start somewhere, you know, a few hundred meters away from the well. And this number, cluster number 4, sort of, as you can see from the histogram here, that one started in May, June, July of 2012. And after that, it didn't have very much activity at all. So just kind of a big burst came for a few months, and that was the end for that one. And then cluster number 5 happened. And so I'm not showing all of the clusters. These ones that are further away are also, they also form later. But I just wanted to zoom in on this zone here, because we continue to look at the induced seismicity data and found some really interesting temporal spatial relationships in the details of the clusters that help us understand a little bit more about what's going on. And then to review, these are the injection periods. So in November 2011, that's when injection commenced in the CCS1 well. Nothing happened for a few months, and then all of a sudden we started to get activity. From November 26th to April 7th, November 26th, 2014 to April 7th, 2017, there was no injection. So I'm going to show you the results, the seismicity, number of events per month for these 3 injection periods. So there was no injection for about 22 months. And then the second well came online at a higher injection rate. All right, so this is the whole injection period from, well, this is not until now, but I went up to 2018 with this histogram, and you can see these I'm going to call them bursts, because that's what seismologists that I'm working with are calling them. But you can see where there's some periods where you get a lot of seismic activity. And so if you compare that to the injection pressure, the downhole pressure and injection rate, it's not really changing. It's kind of the same, except for times when they had to shut down the well for whatever mechanical reasons, things like that. But so these bursts, the point with this is that these bursts of induced seismicity don't correlate with a change in injection rate. And if you look at it in terms of this next phase, is this cyan box here, this is the period when there was no injection. So injection stopped about here. There's still a little bit of induced seismicity, then it trails off to this very low, sort of maybe 10 or less events per month. And if you look at this plot, the events that are dark are the ones that are that occurred during this period. The rest of them are grayed out. So I just wanted to show you that the distribution is sort of all over the reservoir. And then here's the final piece where injection has come back online, and we don't see a significant increase in induced seismicity. And it continues to average around 10 events per month with injection. And again, the injection rate for this second well is about 1.7 times the injection rate of the first well. So this is something that we took and learned, and I'm going to show you. This is just a surface photograph. I'm going to show you a cross-section, well cross-section through these 4 wells, but just to show you where the wells are, the 2 injection, the CCS1 injection wells here, the VW1 verification. This is a pressure and chemistry modeling well, monitoring well. CCS2 is up here, and VW2, the monitoring well, is up there. Okay, so here's my cross-section, and what I'm wanted to show you is that in the first well, because of this induced seismicity, we ended up, this is where we injected just on the top of the Argenta formation there, right? So we ended up saying, well, maybe we should move it up a little bit. So I moved it up from minus 1916 meters to minus 1868 meters. So we're still pretty close to the basement. So that rule about not being close to the basement may not be the whole picture here. And so I took the logs off so you can kind of see more about the wells, and I'm going to put the wells I put the gauges next to the wells. And now for the first injection, I dimmed out the second well because we're not looking at pressure. They're not measuring pressure in that well during injection of the first well. So what I want to show you is what the pressure looks like from the gauges that we measured during injection. This is the highest pressure that was measured at that individual gauge. But somewhere in this one zone right here, the pressure got a lot higher than it did below those gauges or above those gauges. And so we think this has something to do with these things that I marked as light green. These are some very low permeability we call them baffles. They're just little strings where the reservoir properties, where they have a much lower permeability, but they're only a few meters thick. So you can't see them in seismic. You can only see them in the wellbore. And same thing happened when we injected into the second well, where the pressure doesn't increase below the injection zone, but it increases near the injection depth and above, which maybe is what you should expect if you're injecting supercritical CO2, because it should be buoyant. And so I just like to show this because this is, to me, I do a lot of fracture modeling, and I like this reservoir model. I can relate to this because what we did was we modeled the baffles as stochastically, because we have no idea how long they are, how continuous they are. So we just, we match them at the well and then put them all throughout the reservoir. So what this means is that we have a very strong permeability and anisotropy in this reservoir. And this explains the behavior of the pressure from the monitoring wells. Now let's go back to the interpretation of the events and faults. I'm showing here is the events colored by time. So blue is early, red is late. And I'm just showing you this picture to show you, again, when you look at the fault interpretations, it really doesn't look anything like where we have the induced seismicity. And I'm going to skip that. I put that there because I was going to talk about fracture sizes. But they're small, relatively small. And so what I did was I zoomed into one of these clusters or bursts and colored them again by time, a different time scale, so that you can see there's sort of 3 or 4 broad time categories where there was a lot of activity and then there wasn't much activity. And then if you zoom in to even a more coarse more refined time scales than that, you can see that these 3, I said there were 4 time zones. These are the colors that were on the previous cluster. There are 6 hour intervals of microseismicity bursts. And when you look at those spatially, they correlate with different orientations of clusters. So we're looking at these sort of clusters of fractures. It's not necessarily a fault because they cross-cut each other, and you get this activity for 3 hours. It sort of activates this, 100 to 200 meter diameter plane. And this is just to show where the plumes were at the time. So this is the on top of the basement. This surface is top basement, and just a few of the events are above the basement, but they're mostly in the Argenta, the bottom seal that's also not either very thin or fractured. Okay, so what we concluded from this is that mapping the faults could help you if you could identify them. We had a lot of uncertainty at the Illinois Basin Decatur project. We did not identify top seal risk, which was good with the faults, because if you can't see the faults, maybe they are not significant faults. But we did see this induced seismicity, and seeing the induced seismicity was the reason why we reprocessed the seismic data, because we thought, well, we must be missing something. So we went back and reprocessed it and still saw some faults in the reservoir, but we were not able to interpret them in the basement, largely because there wasn't good enough impedance contrast to see if there was displacement, but also because the displacement appears to be very small, like at the resolution of the seismic. The detailed analysis of the induced seismicity, these bursts, I think is very interesting. This is sort of the latest things that we've come up with here. And so it looks like what we're looking at is not reactivation of faults, but maybe reactivation of fracture corridors, right? So if you analyze those those bursts, they have the same sets of orientations as the fractures that we've imaged in the image logs. So they match that orientation spread. And the geomechanical testing, I took those slides out because I thought that was too far down in the weeds, but one of the things that we also see is that these fractures and faults get reactivated at much lower increases in pore pressure than we expected. And so we have laboratory measurements that suggest that the rocks and the fractures are much stronger than they are, but once we start pumping the fluids, they fail much sooner. And so we think that there may be some other things going on, like chemical interactions, that are playing a much bigger role than we originally thought. And that's my last slide. And I just want to acknowledge our partners in research and partners in funding. A lot of work is still going on through the Midwest Regional Carbon Initiative. And so we're trying to make sure that we coordinate with all of the states, from Illinois to all the way to the East Coast, to understand this and apply it to developing other sequestration sites. And the software that I used was Petroleum Experts and Schlumberger. Thank you. Good.